Okay. So tell me what we discussed in the last class. Crystal field theory, and in the evening session we discussed about isomerism, particularly stereoisomerism. In that geometrical isomerism we discussed. So now once again let's have a quick discussion of geometrical isomerism, then we will finish the remaining thing. What is that? Stereoisomerism is there, I will give some clarity on that. Okay, then later we will solve some questions, then we will move for p block elements. Okay, that's it. So first of all, have you written this thing? So now tell me, what are the possible isomers, possible complexes that exhibits geometrical isomerism? I will be giving you some random examples, you tell me. MA5B, will it exhibit? No. MA4B2, will it exhibit? How many are there? 2. So one is cis, another one is trans, like B trans B, B cis B. Okay, in order to show cis isomerism, how that group should be located 90 degrees to each other. Okay, so if they are 180, we can say them as trans. Okay, then next one more thing I told you, MA3B3, here will it be possible or not? Yes. How many are possible? See, in other cases we are saying it as cis trans isomerism. Now in MA3B3 you should say it as facial and meridional. These are the two names you should remember. Okay, then next I have changed these formulas starting with these, then I have written A4BC, here also 2 possibilities are there, then I have went for these, now I am changing here MA3BC, B2C, how many here? Here also it is 3. First this one is 2, this one is 2, this one also 2, the next one is 3. The next what I did here, MA3BCD type, here how many are there? 4. Next MA3 over, A3s are over, so A2, B2, C2, next 5. The next MA2, B2CD 6. The next MA2, BCDE, here BCD 9. Next one is, what is the last one I have given? MABCDEF, here how many are there? 15. So these are the number of geometrical isomers possible for octahedral complexes we discussed. Next, in case of coordination number 4, what are the 2 things I told you? With coordination number 4, we have 2 geometries possible, tetrahedral and square planar. So geometrical isomerism possible only in square planar. So how that group should be? If they are monodentate, they must be like at least A2, B2 type. Okay, for this AA can be cis, AA can be trans, like that 2 possibilities are there. Okay, the next it can also be MA2BC also. Here also 2 possibilities are there, or it can be like MABCD, all 4 are different ligands. Then here how many are possible? 3 possibilities. Is this clear everyone? Okay, now I will be giving you one complex, you just tell me here. PT here, E in twice, ox, not twice, one ox. So tell me here, how many are possible? Is it possible or not? First of all, geometrical isomerism possible or not? See, look at here. In means what are the donating sites? Like NN donors, no? Ox means what are the donor sites? OO donors. Okay, something like it's a bidentate ligand now. This is also bidentate ligand. It means 2 donor sites are there. So it is something like PT, AA, BB type. So I told now about this yesterday's class. Is it possible or not? No. Is it possible or not? So try to arrange. If you are not remembered that, you just try to arrange them. See, I can put this NN donors this side, like E in this side, O this side, like this. Okay, this is cis. It is fine. Now try to arrange them in the trans form. Trans means this NN should be trans to each other, OO should be trans to each other. Is it possible to arrange them like that? See, you need to make a chain from here to here, from here to here, like this. Is it possible? So it means cis trans isomerism is not possible here. Is this clear? The next thing is, one more thing here, I'm just wanted to include here. There is something like this. Metal is there, some metal, and it is like AB 2 times. it means what type of ligand it is? Like two donor sites are there, bidentate ligand only, but one is something like N donor, other one is O donor, something like that, two different donor sites. Yeah, tell me now, geometrical isomerism possible or not? Yeah, try to arrange it once. M, A, B, like this I am putting. Next one, here also A, B. So A, A, how they are? Cis to 90 degrees to each other now. So this is cis isomer, I can say. Now I am placing this as it is, but I am taking it in the opposite manner, I mean reverse of it. So now what happens? A, B, like this. So what about this? B, A. So A, A, how they are arranged now? So it is not to not like remembering something. Based on the given complex, you need to arrange it, whether it is possible or not. See, in this it is possible or not? Yeah. So A are cis in the first case, here A are trans. So you can say this as trans, this as cis. Is this clear, everyone? Okay. Next thing. Now let us move for optical isomerism. See, optical isomerism again here also you should take with coordination number 4 and with coordination number 6 only. With coordination number 1 or 2, 3, 2, 3 it is not possible. Okay, that's where we are starting it from 4 and also 6. Okay, now look at here once again. In order to show optical isomerism, what I am saying, in order to show optical isomerism, or if two molecules are given, they will ask whether these two isomers are optically active or inactive, they will ask. Okay, what to check is they should not have any plane of symmetry. What I am saying, it should not have any plane of symmetry, or it should not have any center of symmetry. So what do we mean by plane of symmetry or center of symmetry? See, plane of symmetry means if you are sending any plane through that molecule, if it is dividing the molecule into two equal halves, then we can say it as a plane of symmetry. So what is plane of symmetry once again? If you are able to pass a plane, that plane, if it is dividing the molecule into two equal halves, then we can say it as a plane of symmetry. For example, I will give you with one organic molecule so that you will feel more clear with that. See, I am writing like this: COOH, COOH, OH, H, OH, H. This is called mesotartaric acid. What is that? Like you will eat tamarind now. Tamarind contains tartaric acid. Okay. So now see, I am just passing a plane like this. Is it dividing the molecule into two equal halves or not? Yes. So I can say this molecule contains plane of symmetry. Is this clear, everyone? Okay. Now here we are talking about inorganic compounds, I mean coordination compounds. Now here also we need to check. See, if there is any plane of symmetry, molecule is optically inactive. What I am saying, if there is any plane of symmetry, molecule is optically inactive. So if you can write, if molecule contains any POS, it means plane of symmetry. Center of symmetry you can write COS, or it is standard form representation is I. I means what? Center of symmetry. Any plane of symmetry or center of symmetry, if a molecule contains any plane of symmetry or center of symmetry, then it is optically inactive. What I am saying, optically inactive. Okay, right. So now with coordination number 4, what are the two geometries we have? Square planar. What you are saying? Square planar. And one more is tetrahedral. See, you are saying the name as itself a square planar. See, if there is a planar molecule like this is a square planar, means it is something like this only, no? So you just take a plane and you try to pass through this gap. Will that divides into two equal halves or not? So it will become two pieces. Yes or no? It means in planar compounds, definitely plane of symmetry will be present. Is this clear or not, everyone? Okay. So square planar complex is optically optically inactive. Okay, it means optical isomerism does not shown by square planar complex. Is this clear, everyone? Okay. Now optical activity is possible in which case? No, tetrahedral, because tetrahedral is not a planar molecule, it is like non-planar one right now. So let us say M I am placing here. Like A, C, like I am writing a complex with MA4 type. Just tell me, see what we have here, MA4 type. Again you just imagine, I already told you about this in the organic also, like this, by taking 4 groups. See, 2 groups are, if this is a central atom, like here it is a metal, these 2 are normal bonds which are lies in the plane. This is above the plane, this red color is below the plane. See, now I am passing a plane like this. Whether it is cutting, what are the atoms it is cutting? This green color, black color. But is it touching anything about this one and this one? No. Now just see the same color. Let us consider these are, both of them are same groups. What I am saying, these are same, both of them are same groups. So just try to cut it now. This and these groups are same means, is it dividing into 2 equal halves or not? So now you just consider all 4 groups are different. What I am saying? All 4 groups are different. So now you are trying to cut it. Now you are cutting it like this. Now what happens? It is dividing into 2 equal halves. But these 2 groups are same or different? So it means, does it have plane of symmetry? If it is dividing into 2 equal halves, then it has plane of symmetry. Now you are dividing into 2 equal halves. But are these 2 groups are same? If they are same, we can say it has a 2 equal halves. If they are different, plane of symmetry is not possible. So it means optical isomerism is exhibits when all 4 groups are different, like M, A, B, C, D. If it is there like this, then tetrahedral geometry shows what? Optically active. Okay. In all other cases, for example, this is the one case. Then example, I am saying MA3B type, and next MA2B2 type. All these are what? Optically inactive only. So which type of isomer is optically active in tetrahedral case? MABCD type. So it is optically active in MABCD type. Okay, which is optically active? Tetrahedral with the MABCD type. It means all 4 ligands are different, then it is optically active. In case of organic, we are saying it as a chiral center, if you remember. Carbon with 4 different groups. Here let us say this is carbon with 4 different groups. Chiral center, so optically active. Like that you can remember. Okay. Is this clear, everyone? Okay. So how it should be, like MABCD type, then it should not contain any plane of symmetry, optically active. Now the example they will give, which are the following is OP active, optically active. So tell me here, which of the following is optically active? Fast. First of all, tell me A is optically active or inactive. So what is the coordination number of platinum here? How many ligands are there? 4 ligands are there. So do you remember, I have given a statement in VBT. All platinum tetra-coordinated complexes and all palladium plus 2 coordinated complexes, tetra-coordinated complexes are always square planar. If it is a square planar complex, molecule itself planar, it means definitely it has plane of symmetry. If it has plane of symmetry, optically inactive. Is this clear? So doesn't mean that like a metal with 4 different groups, it is always optically active. First look at its geometry. What is the geometry of platinum? Square planar. Square planar means no matter whatever the groups present, all groups can be equally divided. Yes or no? I can pass a plane, I can equally divide them. So it is square planar. So OP inactive. What about this one? Nickel is there. Nickel with +2 charge. Nickel +2 means 3d8, 4s 0. So now if you do the hybridization concept, just try it once. If you do, you will get it something like tetrahedral. How it will be? Tetrahedral. So tetrahedral with 4 different groups. Optically active. So this is your answer. Next, what about this? This is tetrahedral, fine. But all ligands are same. So all ligands are same. So OP inactive. Is this clear how we are solving the questions? Okay. Next, this one. Zinc. All four ligands are same. And what about the geometry of zinc? I told you Zn here, zinc +2 means 3d10. 3d10 means only s orbitals are there, p orbitals are, so it will use as s and p, makes it to be sp3 hybridization. So all zinc +2 tetra coordinated complexes are sp3. These statements we have written in the class if you remember. But all 4 ligands are same now. So what I can say it as a OP inactive. Write this fast. So tetrahedral over. Next one is octahedral. So here one point you need to know here is, in tetrahedral case, metal with all 4 different groups. What it is? Optically tetrahedral with all 4 different groups. Does not have any plane of symmetry. So definitely optically active. So optically active. Right now? So similar to that, in octahedral case also, if all 4 different ligands are there, that is also optically active. So here I am writing OP active compounds, optically active or possible. Possibility in offer optical activity, not possible. Okay, I will give some examples. See, what is the first compound I told you? M, A, B, C, D, E, F. So all 6 ligands are different now. So definitely optical activity is possible. So here, if all ligands are same, not possible. Okay. Now let us enter a little more deeper. So now what I am saying, tetrahedral, octahedral means it will be something like this. First it is a square. It's a square now, something like this. It's a square now. So if I only observe square, it has a plane of symmetry like this. Okay. Now octahedral means one line above, one will be below, like this and like this. Right now? Okay. Now you try to pass a plane into this. if if here A, here also A is there. What I am saying, here above A, below A is there. Whatever the groups may be here in the four sides, all four can be divided to halves, like one apple here, one orange here, like that you take. Try to cut it. Will it give equal halves or not? So it means above piece, below piece is same or not? Yeah. So here also A is there, here also A is there. So it means I am writing something like this, MA4B2 type. MA4B2 type I am writing. So all these are A's. Above B, below B I am placing now. So tell me, optically active or inactive? Inactive. Why inactive? Because it has a plane of symmetry. So this is optically inactive like this. Similar to this, even MA3B3 also optically inactive. MA5B, like this, all these are what? Optically inactive. So just remember, with monodentate ligand, this is optically active, and the next one is MA2B2C2 type is also optically active. What are the two things I have told you here? MA2B2C2 type. Next one, MAA2X2. MAB X2 or MAB XY. Next, MAB AA3. Next, MAB3. All these are optically active. What are the optical active isomers I have given? Some examples here. MAA2. AA means what? Bidentate ligand. So just imagine, let us take M. Here A, here A. Here also A, A. It means this is bidentate ligand, it will be like this. Placing here X and X. This is a plane now. So now try to pass the plane. Is it dividing equal halves or not? Yes, dividing equal halves means it should be optically inactive. But I have written here now. You should ask me that why. Here the transform is optically inactive. Trans is, this is cis or trans? Tell me first. How this X and X are adjusted? Trans. So trans is OP inactive. But you need to consider cis form also, no? Cis form means how you will arrange? Like metal. Let us put one AA here like this. Okay, so here one X. Next, here you can put AA like this. You can make a ring. It means if there is a plane, you are making a ring with this thing, and this one no, with these two things. Like that you are making the rings bidentate. Here you are putting what? X and X. Like this, if they are like cis form, it is not a cis form, no, it is trans, no, yeah. So what you need to do is place here A, X and X, cis or not. So this is optically active, OP active. Like that, these are the possible formulas. Now in the exam, they will give a question like this. Cobalt, this is previously asked, in 3 plus 3. Optically active or inactive? This one. This one. What type of complex it is? M in NN type. MAA type. So it is optically active or inactive? Active. So optically active. So for the same compound, they will ask for geometrical isomerism. Cis-trans isomerism. Is it possible in that? You have written in the yesterday's table. No. It is not possible. So optically active, but geometrical isomerism is not possible. No GI, only optical activity. Okay, so this is about complete story of isomerism. Okay, so from isomerism you can expect one question, and from crystal field theory or VBT you can expect one question. 2 questions for sure from this chapter. Okay, so I hope you are clear with this. If you have any confusions or any doubts, always can come to me, you can ask. Okay. Let me check with 2-3 questions how much you are clear about this. Then next we will move for the P block elements first. Over. So what is the order you have written for that that spectrochemical series? Once check it. CO. Tell me first. First is strongest one is CO, next CN, next NO plus NO2, next EN, NH3, EDTA, NCS minus H2O. These are like NCS up to NCS, it is a strong field. Then next H2O, OH minus, like that we have now first fluoride, next chloride, least is bromide and iodine, like that. Weak field ligand is which one? Iodine. Okay. Now tell me what is your answer for this? So which is strongest one? Cn. Here 2 are there. Next oxalate is there. So just compare between F minus and NCS, Cn, NCS minus, Cn, SCN minus. So which is stronger? SCN minus. So option is 2. So purely based on that order only you can expect the question also. Okay. If you know the answer, if you know this order, you can able to calculate, I mean, this kind of questions. You know IUPAC nomenclature, giving IUPAC nomenclature? Yeah. The next one, homoleptic, heteroleptic means you know now, if all same ligands, homoleptic. That is also clear. See, if you know which is strong field, which is weak field, you can answer this question. So cobalt, hexaamine, amine ligands are what? Strong field with cobalt. Fluoride ligands are weak field. So from that, here what is the oxidation state? +3. See, most of the time whenever I solve the questions, I have taken cobalt complexes if you observe. Iron complexes, cobalt complexes, like this, because mostly they will ask on those only. So +3 oxidation state means D6 with strong field ligand. What happens? All electrons will get paired up. So it's a diamagnetic, it is a paramagnetic. So based on that you can solve this. Okay, both statements are correct, I think so. See, this is diamagnetic, it is paramagnetic. Okay, next one. Here you just check this model you haven't seen, I think so. Once read the question. Which complex compound is most stable? Are you able to see the complex compounds? See, first one is all amine ligands, next 4 amine ligands, 1 water molecule, 1 Br. Okay, here 3 amines and nitro groups. See, something like Ma3B3 type. Okay, and this one, last one, if you observe, this one, 2 chlorides are there and EN. So which is more stable they are asking now. If you observe, all of them are with +3 oxidation states only. Once check. All of them are with what oxidation state? +3. So if it is +3 oxidation state, what you can say cobalt +3 means 3d6 4s0. What is that? 3d6 4s0. So it means metals are same oxidation state, means we cannot answer with respect to metal. Now you need to look for the ligands. Now if you see, this is EN now. EN means what? Ethylene diamine. It's a chelating ligand. Right now. So in a compound, more the number of chelations, what I am saying, more the number of chelations, more is the stability. What do we mean by chelation? Rings. So what is a ring formed here? CO, N, ethylene diamine, CH2, like this. So what is the ring size? 1, 2, 3, 4, 5. Like that, this side also you will get one ring. Like this side also, one above chlorine, below chlorine. Like this we got 2 rings now. So more the number of chelations in a compound, more is the stability. Remember this point. Okay? Fine. See, again the ring size must be either 5 or 6. What is the ring size? 5 or 6. If it is a small ring like 3-membered ring or 4-membered ring, it is unstable again. What should be the size of the ring? 5 or 6. Either greater than 6 or less than 5, unstable rings. Remember this. Okay. So due to this chelation, which is more stable? fourth one. In all other complexes, chelation is not possible. So this is highest stability. Okay, what is a single line you can write? As number of chelations increases in a compound, stability increases. Okay, next let me give all the clarity, like is there any other questions here? This one we did yesterday. Can you write the IUPAC name for this? Yeah, see there are two complex things are there, like cationic position also complex, anionic position also complex. So how to write the IUPAC name? Fast. First identify oxidation states. You are getting +2 now, but for this one it is 0. If you calculate normally, it will be +2. But you know, if there are same metals or even different metals also, like this, you need to share that oxidation state to both of them by considering most stable oxidation states. What is the most stable oxidation state for silver? +1. What is it? +1. Okay, so give +1 charge here and here. So now what happens? First write the cationic sphere followed by anionic sphere. So how many aqua molecules are there? So diaqua, so 2 are there. So cationic position means Ag should be called as silver. Anionic position means argentate. What is that? Argentate. So cationic position na silver. So diaqua silver. What I told you? Share that charge. So it is 1, here it is 2. So 1 is better. So 1, next, this anionic, dicyanide. What is a dicyanide or dicyano or dicyanide? Best, see, first you need to prefer iodo complexes. What is the name it should be? Iodo. See, actually in the early, they have given it as cyano, chloro, but later it is updated as iodos, chlorido, bromido. So now what you need to prefer now? Iodos. If iodo option is not there, go for normally chloro, cyano, like that. Clear everyone? Now tell me. So diaqua silver 1, dicyano argentate 1. So this is your name of the complex. Is this clear everyone? Fine. Yesterday at the end we solved this question, energy order. Tell me now. First tell me what are the steps to follow? Oxidation state, metal and oxidation state. Check. All of them are nickel complexes with what charges? Next. So it means now what to check? Ligands. Look at the ligands. Which is strongest? In. More number of ins, where do we have? C. It means greater the splitting. Greater the splitting means more energy gap, more energy absorbed for the transition. So it means energy absorbed will be more for which one? C. After C? Here only one in. More the number of strong field ligands, more is the splitting. So CAB. This is for energy absorbed. So for this particular question your answer should be 4. CAB. This is fine. Okay. Now the same question, I mean 2025 exam, they asked for lambda absorbed. Reverse of it. Anyways you can answer now. Yeah, fine. It's over. EDTA, ethylene diamine with ionic charge. What is its hexadentate with what are the donating sites? It has 2 nitrogen atoms, 4 oxygens. So what are the donors? Hexadentate with 4 oxygens, 2 nitrogens. We have written the structure if you remember. Yeah, that's it. So 31 questions are there. If you are interested you can solve later. Okay, then next let us move forward for P block elements. See, still questions are waiting for you. You can solve all those things. Easy to solve. Okay. So anyways, next one is what? P block. See, in P block elements, I mean chapter, what are the total groups we have? From where to where? 13th to 18th we have. So now 13th and 14th you have studied it, I mean you have studied it as a 11th class, and 15 to 18 as 13, 14 in 11th, these are in 12th. So let us first look into this. See, there are many things to discuss, but I wanted to make it as simple as possible so that we can save our time and it is comfortable for revision purpose also. Okay, so the first one, from 13th group if you observe, EAPCET exam, if I say, the favorite topic for EAPCET examiner is diborane. with a diboron question, I think he won't be satisfied. He will make a question definitely on diboron. So let us look into the topic also. Okay. Firstly, see, questions will be like this based on diboron. I think you have written it for 4 marks or 8 marks. Okay. Anyways, okay, we will come back to this. First let us complete our discussion. What are the boron family elements we have? Boron, aluminium, gallium, indium, thallium. So just remember it as bag it in. What is that? Bag it in. Bag it in. Okay. So now 5, there are like atomic numbers 5, 13, you can remember that. So the next one, first one is, what is that first one? Non-metal. Boron is a non-metal. Next 2 elements are metalloids. Next 2 elements are metals. And last one is radioactive element. Okay. It means what happens to metallic nature down the group? Metallic nature. See, non-metal becoming metals means metallic nature increases. So metallic nature increases, and also metals are electropositive now. So electropositivity down the group, electropositivity increases. Electropositivity increasing means electronegativity decreases. Okay. Now we have studied about periodic trends in the periodic table. What happens down the group size? Size increases, na? Size increases down the group. Okay. So, but there will be some variations in the P block. We will look into it. So, what is the general electronic configuration for these 13th group elements? NS2, NP1. For this, you just take nearest noble gas. What is that? Helium. 2. Next, 2s2, 2p1. For this, it will be 13th means neon. Means 10 over next 3s2, 3p1. Like that, you take the nearest noble gas and write respective valence electronic configuration. Fine? Okay. Okay. So now what are the physical properties? What happens down the group radius, atomic radius? Atomic radius down the group increases. Okay. Particularly if you see from boron to aluminium, aluminium to gallium, like this if you observe, size should increase like this. But what is the electronic configuration here? You have seen 2s2, 2p1. This is 3s2, 3p1 and 3d 0. Here it will be 3s2, 3p1, 4s2, 4p1, and also here 3d 10 electrons are there inside. Yes or no? Okay. So do you remember the order of penetrating capacity or the shieldingness? So which will be symmetric around the nucleus? S, sir. As we move from S to P, P to D, D to F, what happens? That shielding, I mean they have very poor screening effect or very poor shielding effect. It means D orbital also having poor shielding when I compare with S and P. Yes or no? So now what happens? Here D electrons are there. See, atomic number increased up to here. It means positive charge is increasing. Along with the positive charge, electrons also increase. But these electrons have very poor screening effect. Now what happens? This positive charge in the nucleus act on the valency electrons. If they are acting on the valency electron, what it will do? It will drag that, the positive charge drag that valency electron. So what happens to size? Decreases. So that's why gallium size is relatively smaller than aluminium. So what is the reason for that? Due to poor shielding of d orbital electrons. Okay, this is a finalized order. You can write it. Okay, next one. Over this order done? Yeah. Next, ionization energy. Remember it like a W shape. Remember it like a W shape. See, highest ionization energy is for boron. The next one is for thallium. So it is something like a oscillation way it is changing, means it is difficult for remembering exact order. So you make a trick like this. Like this. So what is at the W means this is at the top now. So you put boron here. Next element, aluminium here. Next, gallium. Next here, indium. Next here thallium. So overall order, which is highest top of this W? Next this one now. Next aluminium, indium. So make it like this. Okay. So W shape is for which one? 13th group ionization energies. Okay. Now, what is the general electronic configuration? NS2, NP1. Okay. It means what are the most possible oxidation states they will ask? Yeah. See, boron shows from -3 to +3. Okay. So -3 where it will be, like boron if it is reacting with alkaline earth metals. What I am saying? Alkaline earth metals. So alkaline earth metals means definitely they will be +2 charges. Boron will be negative charge. So here if you do crisscross method, what you will get? Mg +2, Br, B -3, like this. So what is the minimum oxidation state you are seeing? -3. Maximum oxidation state for these 13th group elements? +3. So this is the minimum and maximum oxidation state. So for maximum oxidation state you can say examples like BF3, BCl3, like that. Okay, right. So now most possible oxidation state in the compounds we will see is, you are saying it as NS2 NP 1 electronic configuration. Now if I only remove this NP1 electron, what is the oxidation state you will get? +1. If I remove all 3 electrons, +3. So these are the 2 oxidation states we have, most commonly seen oxidation state. Okay. So what is the highest oxidation state I am saying? +3. Least means if I ask -3, but +1 also possible. Okay. So now out of these 2, which oxidation state is more stable in some compounds? For example here, boron, aluminium, gallium, indium, thallium I am saying. So just take the halides of those. For example, I am taking compound like gallium halides, like any halide you take, and the next indium halide, next thallium halide. What is the oxidation states you are seeing in these 3 compounds? +3 now. So now in +3 oxidation state, which halide or which of this compound is more stable, they will ask. All of them have same oxidation states, same halide ions. How can you decide? So have you heard the word inert pair effect for 2 marks questions in IP? What is that inert pair effect? What is that? The inertness or the reluctance of NS electrons to take part in the bond formation. It means out of this NS2 and NP1, out of these 3 electrons, these inner electrons are there now. They don't want to participate in the chemical reactions. It means which only they wanted to give only 1 electron for bond formation. So now down the group, that inert pair effect will be increases. What I am saying, down the group, it means that bottom element wanted to stay in which oxidation state? +1. Okay, down the group inert pair effect increases. So it means down the group the bottom element wanted to stay in +1 only. It don't want to stay in +3 oxidation state because it is having more inertness for this NS electrons. Why it is having more inertness means, this is bottom element in the periodic table now. Before that element you are going to have F block elements like F orbital electrons. Yes or no? So F orbital electrons have very poor shielding effect now. If they have very poor shielding effect, that nuclear force of element will strongly attract that NS electrons. If they are strongly attracted by the nucleus means, will they participate in the reaction? No. That is what the inert pair effect concept. Everyone clear? So down the group what happens to inert pair effect? Yes. So now the same concept will be applicable in 13th group, 14th group. Okay, wherever we see this kind of halides, inert pair effect means. Okay, so now which halide is more stable? All of them are +3 now. So +3 down the group, what happens to +1 oxidation state? +1 oxidation state increases. If it is increasing means, what about +3 oxidation state? Decreases. It means which halide is the least stable? Thallium trihalide is the least stable. Is this clear? Okay. So there are 2 possible oxidation state First higher oxidation state. So down the group, what I am writing, see, let us make one simple statement. Higher oxidation state decreases stability, higher oxidation state stability decreases down the group. Why? What is the reason? Inert pair effect. I can also say this lower oxidation state, +1 oxidation state stability increases down the group. Is this clear? Okay. It means I am writing gallium +1, indium +1, thallium +1. Which is more stable? Thallium. If I write +3 oxidation state, gallium. Is this clear, everyone? Okay. It is not only halides. It can be anything. In that, what to check? Oxidation state. If oxidation state is +3, gallium is more stable, thallium is least stable. If the oxidation state is +1, thallium is more stable, thallium is more stable, gallium is less stable. Clear? So here I have written anyways. So down the group, lower oxidation stability increases due to inert pair effect. So these are the two orders you need to make in your notes. Okay. Next one, melting points and boiling point. So both decreases down the group. Both melting and boiling point decreases down the group. So which is having lowest melting point if you observe? Gallium. Both melting point, boiling point is lowest for gallium. So due to its low melting point, it is used in thermometers. Where it will be used? Generally in thermometers, what is the thing they will use? Mercury. That silver color if you see, that is mercury. Not only mercury, sometimes what they will be using? Gallium. So high temperature thermometers are there now. In high temperature thermometers, gallium is used. Okay. So gallium, due to low melting point, exists in liquid state in summer. In summer, specifically mentioned as summer. So what is the melting point of gallium particularly? 29.9 degrees. We can approximate it as a 30 degrees for remembering purpose. 30 degrees or 303 Kelvin. Okay, and it is used in high temperature thermometers. Next, move forward. Okay. Next, chemical properties. See, definitely oxygen is more electronegative than 13th group elements, so it will form oxides. What it will form? Oxides. Oxides means oxygen should be -2 charge. Okay, if it is -2, let us say boron is there, +3. So try to do a crisscross, so it will be B2O3. So like that, boron, aluminium, try to form M2O3 type of oxides. Okay, so now down the group, what happens to metallic nature we discussed? Increases. Metal oxides are basic in nature. What I am saying, metal oxides are basic in nature. Non-metal oxides, acidic in nature. Remember, top oxides acidic, bottom oxides basic, because they are metals. Okay, so like that, if you observe down the group, what happens? Basic nature of oxides increases. So top one, B2O3 is acidic, Al2O3 and Ga2O3 is amphoteric. The next two are basic. Okay, and you can expect from oxides, which are the following oxides is basic oxide, acidic oxide. Like that we can expect. So try to write this list. Done? Okay. Next, when it is reacting with water, like 13th group reacting with what? Water. So if boron is reacting, you will get boric anhydride. Boric anhydride is nothing but boric oxide, like B2O3 type. And what is released? H2 gas. Remember, H2 gas is released here. Okay. What is the oxidation state you are seeing here? +3. If I want to do same with thallium, we know down the group +3 oxidation state stability decreases. So thallium don't want to form in +3. So it want to exist in which form? +1. So that's why thallium forming thallium hydroxide. What it is forming? Thallium hydroxide. See, thallium hydroxide is something like KOH or NaOH. Like alkali metal hydroxides are there now, NaOH, KOH we are saying. So these are strong bases now. Similar to that, thallium hydroxide also basic nature almost equals to basic nature of NaOH or KOH. Remember, this is an important point. Thallium hydroxide basic nature almost equals to basic nature of KOH. Next, ఎక్కడున్నావు అందులో? Boron react with nitric acid. Okay, react with nitric acid forms respect to acid like boric acid, orthoboric acid. What is the name of this? Orthoboric acid. Okay, so nitrogen, like nitric acid is reacting now. What is the gas released? NO2. So NO2 have brown color. What is the color of this NO2? Brown gas it is. Okay, even boron react with other acids also, sulfuric acids, HCl, all those things. Here if you see aluminium reacts with acids but does not react with nitric acid. Why it does not react? Because when aluminum is exposed to HNO3, it will form a protective layer. See, if this is an aluminum sheet, if you consider, when it is exposed to nitric acid, only nitric acid I am saying, so it will form a Al2O3 type of oxide layer. It will form an oxide layer. That oxide layer act as a protective one. It means on this top oxide layer is formed. So the bottom, whatever the aluminum is there, will it react? No. So that is why I am saying aluminum does not react with nitric acid due to, what is the term we should say? Passivity. What is that? Passivity. Passivity is nothing but due to the formation of protective layer, oxide layer. Does not it is. Thanks. Okay, over? Okay. Reaction with acid over. First reaction with what we discussed? Water. Next, oxides like oxygen. Like it will form B2O3 type. Next one, acids with water over. Next, acids, bases. Okay. So boron upon reacting with NaOH forms a sodium borate. What it will form? Sodium borate. Here it is boric acid, it is sodium borate. Both contains this unit BO3 3 minus. This unit is called what? Borate. What is that? Borate. So in borate, what is the oxidation state of boron? It is +3. What is the oxidation state? +3. Okay. But whereas aluminum and gallium forms metaborates. What they will form? So there is a difference in the formula. How many oxygens you are seeing here? 3. Here it is 2. Okay. So aluminum gallium forms metaborates. Boron forms borate. I mean metaborate I am saying. It's not metaborate. Meta-aluminate. What is that? This is borate ma. Metaborate means how should be the formula? BO2. So like this formula is there now. So what you should call it as? Meta-aluminate, meta-gallate. Okay. Whereas indium thallium, no reaction. Okay. Indium thallium, no reaction with bases. So once again with bases, with base, boron forms sodium borate, Na3, BO3. Next, aluminum and gallium forms aluminates and galates. Meta-aluminates, meta-galates. Indium thallium, no reaction. Next, when they are reacting with non-metals, what are the non-metals we have, like carbon, nitrogen, like this, no? So carbon forms carbide. Boron upon treating with carbon forms what? Carbides. Okay. Now there is a question like this. Upon hydrolysis of boron carbide, what I am saying, upon hydrolysis of boron carbide, what will be the product formed? So it releases methane gas. What it will releases? Methane gas. So boron converts into boric acid like H3BO3. But they will ask what is the gas released? Methane gas, remember. Next, boron upon reacting with nitrogen forms boron nitrides. What it will be? Boron nitrides. Upon treating with halogens, halides like BCl3, BF3, this kind of compounds are produced. When boron upon treating with like chlorine, BCl3, fluorine, like that. Okay, aluminum upon treating with carbon. So we will get carbides, aluminum carbides. So aluminum carbide also upon hydrolysis, what is the product formed they will ask? here also carbon is there, no? Forms methane gas also. Methane gas only. How many methanes? 3. So aluminum carbides, boron carbides, even beryllium carbides. Which carbides I am saying? Beryllium carbide. All of this gives upon hydrolysis methane gas only. Remember this. Okay. And the next point here itself I want to say, if there is magnesium carbides, what I am saying? Magnesium carbides gives you alkynes, particularly acetylene or propylene gas, like that. What it will give? Acetylene gas or propylene gas. Okay, remember this. Up to here it is over, no? Carbides. Okay. So do you remember inert pair effect once again? Okay. So now tell me, I have all halides like gallium halide, gallium chloride, indium chloride, thallium chloride. Which is more stable? Gallium chloride is more stable because of +3 oxidation state. Okay. Next, when I say particularly about thallium iodide, what I am saying? Thallium iodide. See what I am writing? Gallium chloride, gallium bromide, gallium iodide. Gallium iodide. Which of this halide is more stable? All central atoms are same now. With what oxidation state? +3. But surrounding halogen atom different now. So which halide is more stable, they will ask. Small size halogen, more stability. What I am saying? Small size halogen, more stability. So which is more stable? Like this you can remember. Okay. Now look at this. What I am saying? Thallium chloride is there, thallium iodide is there. Both of them are unstable. But relatively who is more stable? Cl3. This one is more stable, right now? Okay, this is clear. Let us keep it aside. Now it means this is unstable now or less stable now. So actually it tries to exhibit or exist like this with +1 oxidation state, iodine separately as I minus, I3 minus. So thallium, how it will be existing with iodides? Thallium +1, I3 minus. Remember this is important again. So what I have made here, metals upon reacting with halogens forms MX3 type of halides. So stability down the group decreases. Okay. So particularly thallium iodide exists in this form, thallium +1, I3 minus. Okay. Whereas aluminum chlorides exist in which forms? Dimeric forms. It means what is that formula now? Al2Cl6 type. Okay. And here this is again very important topic now. See boron, around boron how many halogens you are seeing? 3 halogens now, let us put fluorines only. So 6 bonds are there. 6 bonds means how many electrons? 3 bonds are there. How many electrons? 6 electrons are there. So 6 electrons means, can I say this is electron rich or electron deficient? So there will be one empty orbital with the boron. So all halides of boron or all 13th group halides are Lewis acids. What I am saying? Lewis acid. They will try to accept a pair of electrons. Okay, all of these are Lewis acids. But which is stronger Lewis acid they will ask. Acidic nature they will ask. So how can you answer? See, generally what we think, this is more electronegative atom, so that makes it to be more acidic, right now? Okay, look at this. But whatever you are thinking now, that is correct, but it won't applicable here, okay? Because fluorine is having lone pair electrons now, boron is having what is the orbital, 2p orbital is empty, here it has 2p electrons as non-bonding, so this will be donated into this orbital. What is this donation called? Back donation now. First they are making a sigma bond. After making sigma bond, now the lone pair electrons of fluorine is given into the empty orbital of boron. So now what happens here? Between boron and fluorine, there is a pi bond formation. See now how many electrons are there with the boron now, check? 8 electrons. Boron is happy now, no? So who will donate that back bonding easily, or who will show that back bonding easily out of these halides? Fluorine. Why fluorine? Because of small size or similar size of fluorine and boron. The back bonding is effective. So due to this back bonding reason, order becomes opposite. So who is good in back bonding? So it means it should be least acidic now. So now what is the back bonding order, you tell me? First BF3, next BCl3, BBr3, Bi3. So now what happens to acidic nature? Reverse of back bonding. So which is strong Lewis acid here? Bi3. So this is the Lewis acidic nature order. Write these two orders, very important. So more back bonding, less acidic nature. Clear up to here? Move forward. Okay. Next one, there are some compounds. First compound is borax. What is that first compound? Borax. What is the formula of borax? Na2B4O7.10H2. This is the formula of borax. When you are writing the structure, you should write it as B4O5. Then next, make it as OH 4 times. How many times? 4 times. How you are making OH 4 times? How many oxygens are there here? I am taking 5 here. 2 oxygens are remaining now. From this 10, you take 2 H2Os. How many hydrogens are there? How many total oxygens we have now? 4. So I am writing 4 oxygens, 4 hydrogens as OH. Next, dot 8 H2O. If you write like this, you will get the structure easily. Okay, I will tell you how to draw the structure, just listen to me. How many borons are there? 4. Put 4 borons like this. Okay, after this, oxygens are 5 now. 1, 2, 3, 4. Fifth one, you put it like this. Like this. All 5 oxygens are over. Next, OH groups. How many are there? 4. So give it to all these borons. Like this, you can give. Okay, is this clear? Okay. Now, what is the hybridization they will ask for each boron in the compound? What is the hybridization of this boron? How many bonds are there? sp2. 3 bonds now, sp2. This terminal boron also, what is the hybridization? sp2. What about this upper and lower one? So sp3. So how many of borons are with sp3? 2. And sp2 also 2. Remember this. Okay, this is how you need to draw the structure. Again, they won't ask in NEET, but in EAPCET. Done? Okay. The next structure is borazine. What is it? Borazine. Also called as borazole. What is it? Borazole. Borazine or borazole. So instead we can also say it as inorganic benzene. What is it? Benzene. Means you know the benzene structure. Similar to that borazine will looks. How many borons are there in borazine? 3. So put those 3 borons like this. How many nitrogens? 1, 2, 3. Connect them. Like this. How many hydrogens are there? Give 1 hydrogen for all the elements. Done up to here? Okay. Nitrogen with 3 bonds means there is 1 lone pair of electrons, 1 pair of electrons. Boron with 3 bonds means there is 1 vacant orbital for each of these, each of the boron and each of the nitrogen lone pair will be there. Okay. So now what happens is the lone pair electrons of nitrogen is donated into the empty orbital of boron. So the structure becomes something like this. B, N, N. So single bond is now lone pairs are giving now. So what happens between nitrogen and boron each time? 1 pi bond. Like this, like this, like this. So how many pi bonds are there? 3 pi bond. Something like, it is something like looking like benzene ring only now. But instead of carbons we have boron and nitrogen. Okay, that's why we are calling it as what? Inorganic benzene. Okay, now what is the hybridization of each boron and nitrogen? sp. How many bonds are there? Sigma bonds? 3. Sigma bonds are 3, so sp2, nitrogens and borons. Okay, yeah. So you can say it as B3N3H6, which is isoelectronic with benzene. What I am saying, it is isoelectronic with benzene. And also structure is same now, and also isostructural with benzene. Isoelectronic, isostructural. Okay. So next we'll discuss about B2H6. What? Diborane. Do it first. Okay, just tell me, diborane means what is the formula you are writing? B2H6. So it means it's a dimer of BH3 unit. So BH3 unit is called borane. What is this? So 2 boranes are there, so we are calling it as a diborane. So you write the boranes individually. How you will write? H, H and one more H. like this. Okay, 3 bonds are there means, see, what is the valency of boron? Like, what is the valence electronic configuration? 2s2, 2p1. It means 1 s orbital, 3 p orbitals. How many boxes we have totally? So each box accommodate 2 electrons, each orbital accommodate 2. So 2, 2, 2. So it means 6 electrons. It means these 3 boxes are used. Okay, one more box is remaining, one more orbital is remaining. So same story with another boron molecule also, like H, here one empty orbital is there. Okay, so due to this electron deficiency, only 6 electrons are there now. Due to this electron deficiency, boron won't exist individually like this. It tries to dimerize into this form. So for that purpose, what happens is, to this empty orbital, the sigma bond contains how many electrons? 2 electrons. All sigma bonds contain 2 electrons. These are also shared to this empty orbital. It means these 2 electrons are shared between how many atoms now? 1, 2, 3. How many atoms they are sharing? 3 atoms. Here also 1, this is donated here. So 1, 2, 3. So boron, H and H. Boron, H and H. In between one hydrogen like this. So you will get a banana here like this. Okay. Now the question will be, how many 2-centered 2 electron bonds are there? What I am saying? 2-center 2 electron bonds. How many 2-center? 2 centers means 2 atoms and 2 electrons. Between 2 atoms, a bond contains how many electrons? 2. Like that, how many bonds are there? All these terminal bonds are 2-center 2 electrons only now, BH bonds. How many are there like that? 4. 4 2-center 2 electron bonds. The next question will be, how many 3 centers 2 electron? 3 centers 2 electrons. This bridged one is there now. So how many bridge bonds are there? 2, like this. Okay. Now what is the hybridization of this boron, they will ask you. So 4 bonds means sp3. Each of these borons in diboron is sp3 hybridized. Remember, important point. Okay. The next one, yeah, just write these points. So sp3 hybridization means planar or non-planar? Like tetrahedral means how it is, planar or non-planar? Non-planar. So the structure of this diboron also non-planar. Like 2 hydrogens like these, bridged hydrogens like above and below, and these terminals will be like this. Okay. So here we have the structure, I will show you. Done up to this? Okay, done. So it is something like this. If you consider this as a plane, bridge bonds will be above the plane and below the plane. Like this you can understand. Okay. Now try to write these internal angles and all. So what is this internal angle? Here we have 97. We have a question on this directly. What is this HBH angle? How much? 97. So what is the distance here? Bridged bond is there now. HBH, bridge bond distance is how much? 131. This terminal, this line is there now, this bond. How much it is? 119. So they will ask you BH terminal, BHB bridge. Which bond length? This is A, this is B. Which is greater, they will ask. Bridge bond is greater now. So you can expect a question like this. Or they will make these angles also. See, boron terminal hydrogens are there now, like this. What is the angle you are seeing here? around 120, that is 119 or 120 you can see. Okay, and inside here 97, and H here, but at the H hydrogen 83. Okay, remember these angles. What are the three angles we are seeing? 120, 97, 83. 120 at terminal BH terminals, 97 at the H center. Okay, no, 97 at, yeah, this is perfect. This is in outside, this one inside. Inside means here. Okay, and what about this one? At the hydrogen. Okay, three angles. Try to remember them. I will show you the question on this. Okay, so you got to know what is the hybridization. sp3 on each boron, and how many BHB bonds? 3 center 2 electron bonds are there? 2. 2 center 2 electron bonds? 4. Now preparation methods we need to know. What are the preparation methods from which we can prepare this diborane? Okay, over up to here, that angles. Okay, look at these 4 preparation methods, 5. With BF3, what? With BF3 and lithium aluminium hydride. So what is the product formed? B2H6. What is that? B2H6. With BCl3 and hydrogen excess, we are doing some dielectric discharge tube we are using there. So what we are getting? B2H6, AlCl3 will be formed here. I mean, this one will be formed as HCl3. So BF3 with the lithium hydride, again similar to the first reaction, it will be giving you B2H6. And these two methods are important. With NaBH4 and iodine, what is that? Sodium borohydride and iodine. What is the product formed? What is the product formed? Diborane. Along with that, what is the gas released? H2. So this is the convenient lab preparation method. So they will ask which are the following is followed in the laboratory method, which are the following is industrial method. Okay, so now same sodium borohydride with BF3. What is that? Sodium borohydride with BF3. Here you will get same B2H6. Where it is used? Industrial. So in industrial method, what are the things used? Sodium borohydride with BF3. Okay, and laboratory method? Sodium borohydride with iodine. Okay, next. Write these 4 reactions, 5 reactions. Okay, let's solve some questions fast. So just look at this. Look at that 4 reaction, that 5 reactions you have seen. In which are the following reaction? Dihydrogen is not evolved. Oxidation of sodium borohydride with iodine. Which method is this? Iodine means laboratory method. What is the products formed? B2H6 and does it release any hydrogen gas or not? Check it. Yeah. Next one, hydrolysis of boranes. What they are saying? Hydrolysis of boranes. It means BH3 hydrolysis. BH3 hydrolysis means okay. So it will be giving you. Okay. We haven't studied about this now. Let's just observe these two things. Heating adduct formed by reaction of ammonia with diborane. Okay. So BH3 is there now. So diborane na B2H6. With what we need to treat this with? Ammonia. So when you are treating this ammonia, first of all B2H6 breaks into 2 equal halves. It means what is formed? BH3. Now BH3 means one lone pair vacant orbital. Like that nitrogen is there now. It has pair of electrons. So it will be donated into this. So it is something like a BH3 NH3. This kind of day 2 bond will be observed. Okay. So is it released in this? No. Next one, burning of diborane with oxygen. So what we are doing? Plus O2. So what happens? It will gives you B2O3. What it gives you? B2O3 plus H2 gas will be released. Okay, because BH3 means B2H6 means hydrogens are there, no, that will be released. So in which reaction it is not released? C. And hydrolysis of boron also releases. Okay, because it forms B3 H3 B3 H3 BO3. What is it? H3 BO3. Okay, along with this hydrogen gas is released. Okay, next. Can you answer me this one? Okay, wait for the question. This one? How much? 97, this is 97, here 120. Next. Tell me here. BF3 with NaH, sodium hydride. Preparation method you have written. So here it is B2H6. Okay. Now that X B2H6 upon hydrolysis H2 gas is released. Along with that, what I told you? B2. What they are saying? Look at the options once. What they are saying? X is an electron deficient. Diborane is electron deficient only, no? Perfect. In X, BB bond is present. In diborane, B2 BB bond is present? No, BHB bond is present. Okay. Next, see here this hydrolysis product is there, na, that is H3BO3. What is that? H3BO3. So H3BO3 means how it will be like this. Like this. How many bonds around the boron? 3 bonds. It means one vacant orbital is there. Okay. So now vacant orbital means definitely it acts as a Lewis acid. So it can be a Lewis acid. So there are 3 protons now. So I can say it releases 3 H plus ions. It means it is an incorrect. Which type of acid this orthoboric acid is? H3BO3 is a Lewis acid, not a proton donor. See, acid definitions you tell me. A proton donor is an acid, electron pair acceptor is an acid, like that we discussed now. Okay, so what type of acid it is? It is a Lewis acid, not a Bronsted acid. Okay, what type of acid is it? It is, it means what? It will accept a pair of electron. See what they are saying, Y is a weak tribasic acid. Is this correct? So tribasic, monobasic means what? See, HCl is there. How many H plus ions it is releasing? So it should be called as monobasic. Sulfuric acid is there. How many it is releasing? 2. So dibasic. They are saying this as a tribasic. Will it release as 3 H plus ions? What I told you, it's not a, it won't release as H plus ions. So it means it's not a tribasic. So it does not contain this thing also. Next, Y act as a Lewis acid. Correct only, no? So what are the two options? 1 and 4. This one. Okay, next. As an extra part discussion, you just need to look into these things. So borazine structure we have discussed. Okay, so here borazine structure done, already we discussed. Diborane with excess of ammonia. What I am saying, diborane with excess of ammonia at higher temperature gives you boron nitrides. What it will gives you? So boron nitride is also known as inorganic graphite. What is like graphite we know now? The pencil leads. So instead that we can say inorganic graphite. What is the formula? Boron nitride. About graphite we will study in the next class, it means 14th group elements. Okay, done with this. See, diborane with excess ammonia, what is the product? Previously I told you, diborane with ammonia only, just mention ammonia. What it is happening? Diborane break into two equal halves, BH3 and NH3, like a day 2 bond will be there. Okay, it means the product formed identified by looking at the amount of ammonia we are taking. Over this last reaction. One last discussion here, small discussion is there. So just read that points. Diborane is a colorless gas. It is rapidly decomposed by water by formation of H3BO3 and H2. So this is a reaction. We see in one question on that. Okay. So now mixture of diborane with air or oxygen catches fire spontaneously, producing a large amount of heat. Next, diborane has a higher heat of combustion per unit weight of the fuel than most of the other fuels. Therefore, it can also be used as a rocket fuel. So, what is the applications of diborane? It is used as a rocket fuel. Why it is used as a rocket fuel? Because it is having high heat of combustion. It means what? When it is burned, it is producing high amount of energy. That's why it is considered as the best fuel in the rockets. Okay, this is the energy it is producing. Okay, per mole. Okay, so now you can see the cleavage of diborane. This reaction is again important. So the first one, diborane. See, diborane with what they are treating? Trimethylamine. So trimethylamine also means here lone pair electrons are there. So break this molecule into two equal halves. BH3 unit. To each BH3 unit provide these two electrons. So what happens? A complex like this it is formed. Easy to remember. Diborane breaks into two equal halves like BH3 units and attach this trimethylamine. Trimethylamine. That's it. How many it will be? 2. Okay. Next, same diborane with CO. Same like diborane with carbon monoxide. Okay, here also break into two equal halves. Lone pair electrons and carbon are there now. That will be given to the each of the borane. So it will also form similar type of product. Okay, next. Diborane like B2H6 with ammonia here. It is trimethylamine, this is ammonia. First, in the previous case I told you, forms BH3 unit, NH3 unit. Here what is happening when we are taking like this? It will forms BH2, NH3 twice. BH2, NH3 twice like this. Out of these, how many borons are there? 2. One is forming BH2. You break these as BH2 unit and another one is BH4 minus. So BH4 minus exists independently. To this, what are the two things coming inside? NH3s. Okay, so NH3, two things. Okay, so this upon heating, what you are going to get? B3N3H6. What is this B3N3H6? So preparation of borazine you have studied. So along with that, what is releasing? H2. Once again tell me, what is the procedure for borazine preparation? B2H6 treating with 6 NH3 units forms a adduct first, intermediate, that upon heating gives you borazine. Okay, next. In the above reaction, borazine is formed and it is known as inorganic benzene. Okay, fine. Up to here everything is clear. So we need to discuss about 14th group elements. Okay. So tell me, what are the 14th group elements we have? Let us solve the questions otherwise. Okay. With the whatever the concept you know, you just tell me, answer me this, because if I start it also, it won't be over. So just tell me for this question, EAPCET question it is. For which of the following +3 oxidation stable state is highly stable, highly oxidizing character? Once again read it. Not stability. They are not asking about stability. Once again read it. For which of the following +3 oxidation state? +3 oxidation state is highly oxidizing in character. Highly oxidizing means what? It should oxidize as others, undergo reduction. So undergoing reduction means if a species is not stable in that +3 oxidation state, it will undergo reduction. So tell me, which is not stable in +3? Thallium, no? So which is strong oxidizing agent here? See, +3 is unstable, no? Unstable means what it will do? It will try to come for +1. So now what happening to this species? If it is undergoing reduction means species reacting with this will undergo oxidation. So which is having high oxidizing character? Thallium. Okay, like this you can answer. Okay, next question here. We'll see this in the next class. Yeah, can you match these questions? You know about diamond and graphite? I think you studied. Based on the knowledge you have, you just answer me this. Diamond is covalent, graphite is ionic. No, both of them are covalent. Next, diamond is sp3 hybridized, graphite is sp2. Correct only, no? Next, both diamond and graphite are used as a dry lubricant. No. Which one is used? Graphite. Okay, next, diamond and graphite have two-dimensional framework. No. Which one? Diamond has three-dimensional. Yeah, next. So which is correct here? Only second option. Next, these are NEET questions. Yeah, this one you tell me. Graphite is? Do you know anything about fullerenes? Like you have seen from the 10th class, you are seeing them. Like footballs, buckyballs, they will say. Okay, let us finish the discussion here itself. See, carbon has three isotopes, three allotropes. What are the three allotropes of carbon? Graphite, diamond, fullerene. Okay, so fullerenes generally, how the fullerenes are formed? When you are heating graphite, what you are doing? When you are supplying high temperature to the graphite, it will give you sooty flame. What is that? It will give you black soot will be formed. In that black soot, they have observed there are something like C60 compounds, C70 compounds, C80 like this. So what is this? All things are considered as fullerenes. So now these fullerenes, let us say C60 is a major component here. So it contains, it is just made up of hexagons and pentagons. What it is? It is made up of hexagon, pentagon. In all these fullerenes, whether it can be C60, 70, all these things, there will be pentagons. What I am saying? Pentagons. How many pentagons? Pentagon means 5-membered rings. How many there will be? 12. How many are there? 12. This number is fixed for pentagons for all the compounds. Okay. Hexagons for C60 is 20. How many hexagons are there? 20. So just tell me how many again? Pentagons are how many? 12. Hexagons are how many? There is a PYQ, that's why I am saying this. Okay. Now if they ask for C70, how many pentagons will be there? I am saying pentagons will be fixed as 12 only, but hexagons changes. Hexagons changes. So there is a formula or a tricky way to remember this. So Cn or n minus 20 by 2, you use the formula. What I am saying? N minus 20 by 2. What this n represents? Number of carbon atoms. For example, let us apply it for C60 only. How many hexagons I am asking? 60 minus 20 by 2. 40 by 2. So it is applicable now. So can you tell me for this C70 how many hexagons are there? 70 minus 20. 50, 25. So 25 hexagons, pentagons. Remember this, how to identify number of pentagons and hexagons in a given thing, in a given fullerene. And what is the use of fullerene, they will ask. So it is used in cancer therapy, where it will be cancer therapy. It means these are nothing but a tubes, like fullerene tubes, like this it will be. Okay. So now these tubes are that you are seeing it as a buckyball, like football, like that, no? So now they will send that tube or whatever the buckyball, whatever it is, to the patient body. So they will block that cancer or whatever the thing is there. Okay. And they will block it. So like that they will remove it out. So that's why used in the cancer therapy and all. Okay. Remember all these points. Yeah, that's it. Remaining thing we'll discuss in the next class. So just to summarize once what we discussed. Huh? Clearly.